Welcome back. So today I'm going to derive the Reynolds average Navier Stokes equations for the momentum part of the Navier Stokes equations. Last time we saw how we could take our turbulent velocity field u, which is a function of space and time, and we can decompose it into a mean flow field, an average flow field, time averaged, plus all of the turbulent fluctuations that vary in time. And when we take this Reynolds decomposition and plug it into the Navier Stokes equations, we can get simpler expressions or simpler equations for the mean velocity field components, which might be what we care about as engineers. If I'm going to design an aircraft or a wing, I might just care about the average drag or the average lift. And I might not want to or be able to afford to simulate all of these turbulent fluctuations. I might want to average those out and just see how they affect the mean, kind of the bulk flow quantities. And last time we did this by taking the Reynolds decomposition, this kind of mean plus fluctuations, and we plugged it into the mass continuity equation, the divergence of u equals 0 equations. This should be a vector u. And we found by pretty simple arguments that from this equation, the divergence of the mean flow had to be 0, and the divergence of the fluctuating components had to be 0. And so we're going to do the same thing today, but for the full momentum equation up here, which is a lot hairier, a lot more complicated. Okay? So I'm kind of looking forward to this. This is going to be one of the most involved kind of mathematical derivations I've done on this board. I think we're going to fill up the whole thing. So I'm pretty excited to get started. This is going to be a workout. This is like going to the gym or eating your kale. It's going to make you stronger, and I know that we all love kale. So let's jump in. And I'll also point out, I'm not actually going to derive the entire vector momentum equation because it would be way too big for this, this setup. So what I'm going to do is I'm actually going to show you how this works for just the u or x momentum, the first component of this momentum equation. And we're going to plug this decomposition into the first row of this vector equation. And so kind of in components, the equation I'm going to solve or write down is u sub t. This is little u, the first component of the velocity field, plus, and this convection term, we can essentially write this as u partial partial x plus v partial partial y plus w partial partial z or z, depending on which side of the pond you're on. All of that applied to little u equals minus partial partial x of p, okay, minus partial p partial x plus 1 over the Reynolds number, the Laplacian of the first component of u. So del squared of little u here. So I'm just solving this for the x component, the first component of the momentum equation of my Navier Stokes. That's just the first row of this vector equation I've written down here. And we are going to plug in the Reynolds decomposition. We're going to plug in this expression here for all of the terms, expand it out, and we're going to time average and see what terms drop out. We're going to see if we can get a simplified expression just in terms of the mean flow. Great. OK, so let's do it. Can't stall when you're deriving the RANS equations. So for u sub t, little u is u bar, the average u, plus u prime. So this is, and I'm going to give myself a little place to work here, so right here. So I have u bar sub t plus little u prime sub t. And subscript here is going to be partial derivative with respect to t. OK, good, plus. Now, every single one of these terms, this u partial partial x is really going to be big U bar plus partial partial. Sorry, let me slow down. This is u partial x plus v partial u partial y plus w partial u partial z. And so for this u and this u, I'm going to be plugging in u bar plus u prime. OK, good. And I'm going to get a bunch of cross terms. Just like when you multiply polynomials, x plus y squared, you get the cross terms. We're going to get a bunch of cross terms here. This is going to be the nastiest part of the expression. So let's try this out, and let's hope I can get this right. So this is u bar u bar sub x, that's just partial with respect to x, plus u bar little u prime sub x, plus little u prime u bar sub x, plus little u prime sub x. That's what I get if I take u bar plus u prime and I plug it into this first term, u bar plus u prime, partial x of u bar plus u prime. And I do the same thing for the second term and the third term. Okay, so now I'm going to have plus v bar, u bar, now it's a derivative with respect to y, plus v bar little u prime sub y, plus, plus v, u bar, good, plus little v prime, u bar sub y, plus little v prime, u prime sub y. This is hard to keep all of this going, so please, follow along and yell through the screen if I get something wrong. Okay, plus now we have to do for the w component, and I'm hoping I can just do this by pattern matching. W bar u bar sub z plus w bar little u prime sub z plus little w prime, my fluctuations in the w direction, u bar z plus little w prime little u prime sub z. That's just my convection term. And now I have these last two terms, my pressure gradient and my viscous diffusion. So that's a little bit easier. And I'm going to say all of this stuff equals, and it equals minus p bar x minus p prime x plus 1 over my Reynolds number del squared of u bar plus 1 over my Reynolds number del squared of u prime. Okay, that is step one. So step one is to take my Reynolds decomposition, plug it into the x component of my momentum equation, and this is all of the terms that I get. But fortunately, a lot of these terms are going to die really, really quickly. Okay, so they were not meant for this world. So this u bar is, by definition, we've averaged time out. This does not vary in time. So when I take its partial with respect to time, that's 0. And now the next step is essentially we're going to time average this entire equation. We're going to time average every single term in this equation. And we're going to use these identities here to kill as many terms as possible. Okay? So, and there's two equations that I'm going to use extensively. I'm going to use this one and this one. And I guess I'm also going to use this one. Well, I'm using all of them, to be honest. I guess I'm using all of these. So the time average of this entire equation is the sum of the time averages of every piece. That's this term. Anytime I see a lone u prime and I time average it, I can kill it, even if it has a partial derivative, because the time average of a partial derivative is the partial derivative of the time average. Now, you're going to have to take your time and convince yourself of these last two. Just get a big sheet of paper and try to work this out and convince yourself that these are true. But it allows me to kill this term when I time average. And when I time average my u bar x, nothing changes because the time average of a time average is just the same time average. So this is unchanged. This is unchanged. Any term that has one average component and one fluctuating component, when I time average it, it is the product of the time averages. And the time average of u prime x is 0. So this term is 0. This term is 0. All of the terms that have a single fluctuating component are 0, which is huge. We just killed like half of our terms. My pressure prime fluctuation is going to die out when I average. My Laplacian of u prime is going to die out when I average. And these become average, average, average. So this is my time averaged, Reynolds averaged Navier Stokes equation for the first component of my momentum equation. So right off the bat, I've eliminated most of the terms. I just have a few terms left. And so I'm going to group those kind of over here. And we're going to see if we can simplify even more. OK? So let's do that. And I want to make sure to kind of get this right. This is really important. So over here, I'm going to write that I have u bar x. I'm going to first group all of my average terms, all of my mean flow terms, plus v bar u bar y plus w bar u bar z or z, plus all of my fluctuating components, plus little u prime x time average, plus v prime u prime y time average, plus w prime u prime z time average. OK, these are all of my turbulent fluctuating components. Notice these didn't go away. This is actually troublesome. I wanted an equation just in terms of mean flow components, but I have these pesky turbulent fluctuations here, and these are not 0. The average of products of primes are not 0. Very important. I should put that here. U prime squared average is not 0. Super important. Okay, again, convince yourself that this is true. These are essentially the variances of the turbulent fluctuations. The average turbulent fluctuation is 0. The variances are absolutely not 0. They have variance. That's the definition of turbulence, pretty much. OK, and then there are two more terms. This equals my pressure gradient minus p bar x plus 1 over the Reynolds number of the Laplacian of u bar. So this is a much, much simpler equation. Right off the bat, there is no time-varying term. This doesn't vary in time. These are all averaged to quantities. So if I knew what these turbulent fluctuations were, I could solve for my mean flow variables, and I could get my average drag or average lift on my wing. Okay? But these quantities here are a real pain. These are called Reynolds stresses, or they're related to Reynolds stresses, because they kind of have the units of a stress. And I'll get to that in a minute. But what we're going to do now is we're going to try to simplify these three terms and make them a little bit easier to work with. So this is kind of step 2. We killed a bunch of terms and we grouped them. Now step 3 is I get to simplify this using essentially a chain rule identity. So I'm going to do that now. It really makes my life a lot easier, so please bear with me. Okay? So down here, we're just going to try to simplify those terms. And what I'm going to do is I'm going to say I have u prime x, that's this term. I'm going to have v prime u prime y and w prime u prime z. Of course, time average all of them. And I'm going to set these each equal to something where the second term is going to add up to 0. So I'll just show you. So this is partial u prime, partial x, all of that time averaged, minus u prime, partial x. Again, all of that time averaged. Sorry, this is getting a little crowded. This is just the chain rule. If you take this term, partial u prime squared, partial x, then essentially it is 2 u prime, partial x. That's 2 u prime, partial x. So these are equal. And if I move this over here, I get 2 of them. And that's just the chain rule of this guy. Same thing, I can chain rule this one. And I get that that is the partial of v prime u prime with respect to y, time average, minus, I guess this would be a u prime partial v prime partial y, time average. Again, if I chain rule v prime times u prime with respect to y, I get v sub y u prime plus u sub y v prime. So if I add these up, I get that by the chain rule. And then the last one similarly, sorry, this is just, trust me, it's going to make our lives easier, and it's going to make it much clearer what this term is. The last one is just partial w prime u prime partial z averaged minus, I guess, u prime partial w prime partial z averaged. But here's where it gets kind of interesting. If I take these three terms here, the u prime partial x, u prime partial v partial y, u prime partial w partial z, all of this added up, because we're adding these three up, all of this added up is u prime times the divergence of vector u prime. Little component u prime times the divergence of the vector uvw. And we know from the last lecture that the divergence of the fluctuations is 0. So this whole term equals 0. These three terms add up to 0. So the sum of these is the same as the sum of these. So that's where it gets really nice, is I'm going to simplify this, and I'm going to write down that these three terms here are just u prime average partial x plus u prime v prime average partial y plus partial z of u prime w prime. That's what these three terms become. And I still have my other terms. I still have my u bar x plus v bar u bar y plus w bar u bar z. And all of this equals minus p bar x plus 1 over Reynolds number of Laplacian of u bar. This should be a big U, whatever, it doesn't matter. U bar. OK, good. So now we have finally arrived at the kind of expression I wanted, which is we took the Reynolds decomposition, we plugged it into the Navier Stokes equations, the first component only here, and I time averaged to kill most of the terms. We collected the terms that stayed alive here, and we have these pesky terms that contain just these fluctuating turbulent components. We use some math identities here to simplify. We basically use the divergence-free part of the fluctuation components to get this final expression. This is the Reynolds average Navier Stokes equations, at least the first component of it. You could do this for the second component for little v sub t, the third component for little w sub t, and you would get 3 of these big equations. Now here's the part I really wanted to get to, which is this equation is almost exclusively in terms of mean variables, averaged variables, the bulk properties of the flow that I want to know about, like my average drag and my average lift are going to be computed from. But I have these pesky terms here. These are called the Reynolds stresses. These are my Reynolds stresses. And they stress us all out in turbulence modeling. In fact, it's literally the u prime bar. That's a Reynolds stress. U prime v prime bar is a Reynolds stress, and u prime w prime bar is a Reynolds stress. Because when you take their gradient or their partial derivatives with respect to space, you get a term that has the units of force per volume, just like these stresses. So you can kind of move these terms down here, and they act to force the mean flow variables kind of how a stress would. And so the whole game of turbulence modeling, the whole strategy of Reynolds average Navier Stokes and other turbulence modeling is to try to approximate these quantities, which depend on the turbulence fluctuations. I need to know my u prime of space and time. This is a mess to compute. Can I approximate these Reynolds stresses in terms of the mean flow? And it's only going to be an approximation. It is not going to be exact. We're going to lose information. But if I can approximate these Reynolds stresses in terms of these mean flow quantities, then I have a chance of actually solving this for u bar, v bar, and w bar, which tells me a lot about the bulk properties of my engineering flow. Okay, so we're going to go way more into depth, kind of deriving some of these closure models, looking at what are some of the models for these turbulent fluctuations and these Reynolds stresses in terms of these big bulk mean flow properties. And then we're going to look at how you can start using deep neural networks and machine learning to get these closure models from data. So that's all coming up. It worked.